Beings on this strange spherical asteroid that has a radius of 3.852 times 10 to the 6 meters have observed that a large rock is approaching their asteroid in a collision course. At 7,514 kilometers from the center of the asteroid, the rock has a speed of 136 meters per second, and later, at 2,823 kilometers from the center of the asteroid, it has a speed of 392 meters per second. So A is asking us to find the mass of the asteroid. Okay, so let's draw a picture of what's happening here. So we have this asteroid. Okay. It's called some weird symbol, maybe pi. And the radius of the asteroid is 3.852 times 10 to the 6 meters. And 7,514 kilometers from the center of the asteroid, okay, let's say over here, 7,514 kilometers from the center, there's a rock, and it has a speed of 136 meters per second. And later, as it gets closer, say over here, when it is now 2,823 kilometers from the center, its velocity is now 392 meters per second. Okay, so the question is asking us to find the mass of the asteroid. So we're going to use energy conservation as is suggested in the question. And we'll say the total energy that the asteroid has initially is equal to its total energy final. So we'll say up here is initial, and when it's at this point over here, we'll say that's final. Okay, so what type of energy does this asteroid have? So initially it has a velocity, so it does have kinetic energy. And it also has gravitational potential energy. Since we're not near the surface of the Earth, though, we can't use the simple formula for gravitational potential energy, mgh. We need to use the long formula. And remember, for that long formula, the one that's negative g m1 m2 over r, for that equation, the reference position is infinitely far away. That is when the gravitational potential energy is equal to 0. So if you're not infinitely far away from the surface of the object, so in this case from the surface of the asteroid, then you're going to have a gravitational potential energy. So we will have that UG initial equals, in the end at the final position, it still has a velocity, so we still have kinetic energy, and it's still not infinitely far away from the center of the asteroid, so we'll still have a gravitational potential energy. So let's put in all the formulas. So EK initial is 1/2 mv squared. UG, we need to remember there's a negative sign here. G m1 m2 over r equals 1/2 mv final squared minus again G m1 m2 over r. So when we're talking about the mass over here in the 1/2 mv squared, we're talking about the mass of the object that has a velocity. So that would be the mass of the actual rock. The question is asking us for the mass of the asteroid. Okay, this is the mass of the rock. The question does not tell us anything about the mass of the rock, so I'm just going to leave that as m rock. In the second term, g m1 m2 over r, that mass, those two masses, one is of the rock, the other one is of the asteroid. So I will call it m of the asteroid here. For the velocity, for the kinetic energy, that mass is the mass of the rock because that's the object that has the velocity. And again, we have m1, which is the mass of the rock, and mass of the asteroid over here. Okay, so notice there's a mass of the rock in every one of those terms. So I could divide everything by mass of the rock, and that goes away. So that's good because the question didn't tell us what the mass of the rock was. So we're trying to find the mass of the asteroid. And we know everything. We know the r, so I'm going to put r initial and r final. So our r initial was 7,514 kilometers. We need to change it to meters. And our r final is the 2,823 kilometers changed to meters. Okay, so I'm trying to find out what the mass of the asteroid is. So I'm going to put everything that has a mass of an asteroid on one side of the equation. So I'll bring this over here to the other side of the equal sign. So I have g, mass of the asteroid, over r final minus g, mass of the asteroid, over r initial, equals, and now I'm going to bring the 1/2 v squared to the other side of the equation. 1/2 v final squared minus 1/2 v initial squared. Okay, again, I'm trying to solve for mass of the asteroid, so I'm going to factor it out. And now I'm going to solve for mass of the asteroid. Okay, now I'm going to plug everything in. 1/2 v final. So this was my v final, 392 squared minus 1/2 v initial, which was 136 squared, over g. G is my gravitational constant. It's always 6.37 times 10 to the negative 11. No, 6.67. Over r final, which was 2,823, but I have to change it to meters, so it's 1,000, minus g over r initial, which was the 7,514, change to meters, and now I can type everything into my calculator. And I get 4.582 times 10 to the 21. That's a mass, so it's in kilograms. Let's look at our units, our significant digits. So I have 4 significant digits, 4 significant digits, 4, 4, and 4. So my answer should have 4. So I'm good. Okay, so that was part A. Part B, it says, a being fires a rocket straight away from the surface of the asteroid. With what minimum speed does the rocket need to escape from the gravitational pull and never return? Okay, so this question's asking for the escape speed. So what happens here is, let's say I'll draw this picture over here. Let's say the rocket is here and I shoot the rocket out with an initial velocity. If that velocity is not high enough, the rocket's eventually going to slow down and come right back to the surface. But if that velocity is high enough, that rocket is going to reach an infinite distance away and never come back. So in order to figure out what the escape velocity is, you need to know that the initial velocity that the rocket reaches is going to be 0, but it's going to the final velocity is 0 when the final distance from the center of the planet, or in this case the asteroid, is infinity. So that means that the rocket made it infinitely far away, but it just barely got there and came to a stop. Okay, so those are the conditions to find the escape speed. So I'm going to still use energy conservation. This is part B. And I'm going to say E total initial equals E total final. Okay, so we're looking for the initial velocity of this object over here. So this is initial, and final is out here infinitely far away. So when you're at your initial position, you have a velocity because that's the velocity you're trying to get it to escape with. So you're going to have kinetic energy. And you're also going to have gravitational potential energy because remember, the reference position where gravitational potential energy is 0 is when you're infinitely far away. So when you're on the surface of the asteroid, you do have gravitational potential energy. In the end though, EK final and UG final, in the end, when you reach that infinitely far away position, your velocity is 0, so that means your kinetic energy is 0. And your gravitational potential energy is also 0, because remember, the reference position where gravitational potential energy is 0 is when you're infinitely far away. And that's because the formula for gravitational potential energy is negative g m1 m2 over r. So when this is infinitely far away, so r is infinity, when you divide by infinity, you get a very tiny number, and it approaches 0. So both of those terms go away. I'm going to plug in the formulas. EK initial is 1/2 mv squared. UG, gravitational potential energy, is negative g m1 m2 over r equals 0. So what are these masses then? This mass is the mass of the rocket that you're trying to get to escape. In the next term, m1 and m2, one of these masses is the mass of the rocket. The other one is the mass of the asteroid. Okay, and then r is the initial r in this case, so that's the distance between the center of the asteroid and the center of the rocket, which would just be the radius of the asteroid. So I'll just call it RA. I'm looking for the escape speed, so that's my v initial. So I'm going to rearrange the equation, but first I notice that I have a mass of r in each term, so I could just cancel it out. Mass of r goes away. Okay, so I can solve for this v initial here. I'll bring the GMA to the other side of the equation. I'll multiply both sides by 2. And then I'll take the square root. V initial equals the plus or minus square root of 2GMA over RA. But we're looking for the speed. We don't need to worry about the minus here, so I'm just going to get rid of that plus and minus. And now I can plug everything in. So I have 2, g is 6.67 times 10 to the negative 11 times the mass of the asteroid, which we found in the first part was 4.582. I'm going to give some extra digits. 4.58178 times 10 to the 21 divided by the radius of the asteroid, and it tells us the radius of the asteroid right here, 3.852 times 10 to the 6 meters. Let me clean this up. Okay, so here's the radius, 3.852 times 10 to the 6. And I'm going to type everything up here. And I get 158,673 meters per second. Now remember, I want everything to be, oh, and I forgot to square root it, so I'm going to square root all of that. And I get 398.3 meters per second. Okay, remember I wanted everything to have 4 significant digits, so I'm all good here. All right, thanks for watching.